Welcome back. Today we're going to talk about nuclear chemistry. It's a bomb! Yeah, that doesn't go over that well in person either. So the difference between nuclear reactions and chemical reactions that we're going to look at, this will probably be the only time we really look at what's happening internally in an atom this semester. It'll be on the final, but most of the semester we're going to look at electron transfers or electron sharing. So a nuclear reaction changes an atom's nucleus. So we are not going to talk about after chapter 22, we're not going to talk about changing the nucleus at all. So we're going to be changing the internal structure. And when you do that, there's a lot of energy involved and sometimes some very negative consequences or positive consequences depending on what you're trying to do. So in this chemical reaction, there's going to be a change in the way that the different atoms are combined, but mostly we're actually changing what is like how many protons, how many neutrons, or how many electrons are actually in the atom, but mostly looking at changing these two are going to be different than what we do the rest of the semester. Now, remembering different isotopes of these elements have essentially the same behavior, they just have a slightly different number of neutrons. So they can have completely different behavior in nuclear reactions because nuclear reactions are looking at changing the number of protons and neutrons. We're changing that nucleus in some way. So we're not going to be really looking at moving electrons around during a nuclear reaction. We're looking at, remember that center of the atom has the protons and the nucleus and the neutrons. So this is the protons and the neutrons. But the electrons are out here in the electron cloud, and that's going to be later in the semester. Well, coming up soon. So different isotopes can actually have completely different types of nuclear behavior. The energy change is immense. I mean, it's far greater than anything that we could imagine for a chemical reaction. So we have very, very big energy changes. Remembering that radioactivity, this is our spontaneous decay. I mentioned this just a little while ago when we were talking about J.J. Thomson and discovering the electron and where they get these particles from. So when you have a radioactive substance here, it's going to spontaneously emit radiation. It can emit different types of radiation. Remember, beta radiation is negatively charged. They're going to flow towards the positive electrode. Alpha radiation is going to be positively charged and flow towards the negative electrode. And gamma rays is undeflected. They're going to go straight through because they're neutral. So alpha and beta can actually be deflected much easier than gamma, and gamma can actually do more damage. So gamma rays aren't affected and they have no electric charge. They're going to go straight through, but sometimes they can go straight through and they can go through further and cause more damage. So this is alpha radiation. You're going to need to know a general reaction for each of these, but this is very specific. So you need to know what alpha radiation is. An alpha radiation is an alpha particle. It is specifically a helium-4 nucleus. So when I say helium-4, I mean helium with a mass number of 4, and helium has an atomic number of 2. So this would be the nuclide symbol. So we have 2 protons and 2 neutrons in the nucleus. And that's what's really important in these nuclear equations, is going to be looking at what changes here. How many protons and how many neutrons are changing in this is what's going to matter. So this is going to be an alpha radiation where we're giving off an alpha particle. This is an alpha particle. You need to know that. You must know this. And for the final, you're going to need to know that. So when uranium emits spontaneous, it starts to spontaneously decay, it's going to emit alpha particles, which is a helium-4 nucleus. So it emits this helium-4 nucleus, and because this is on the other side of the arrow, remember the conservation of mass tells us that these 2 blue numbers must add up to this blue number. So if we took away 4 to get that helium nucleus out, so we subtracted 4, we must end up with 234 because 238 minus 4 is, so 238 minus 4 gives us 234. Let me erase this. So 238 minus our helium nucleus gives us 234. So we know our product is going to have a mass number of 234. But what is the Z going to be? So we need to know what the Z is going to be. Well, starting with 92 with uranium, we're going to say 92 minus 2 gives us 90. And then we'll look on the periodic table for element number 90, and in this case, it's thorium. TH. Okay, so this isn't too hard to figure out actually what happens. You're going to want a periodic table handy, right? So you can look up number 90 and you can say, well, gosh darn, that's thorium. Okay, anyway, so this is an alpha particle. This is the symbol for alpha. Moving on. A beta particle is an electron. So sometimes you'll see this written like this. You might also see it written like this, beta negative. So negative, meaning that this is a negative electron. We'll talk a little bit about a positron in a moment. So this is going to be a little different for the math. Let's do the math in a different color this time. I'm starting with iodine 131. So when I go over here, and this is going through beta radiation, in my head, beta radiation needs to say that's giving off an electron. So I know that this is the particle. So you have to know this. All right, so beta radiation gives off this particle. So if we're starting with iodine 131, we're going to say 131, and since it's on the other side of this, we're going to subtract it, minus 0. So it's going to have a mass number still of 131. All right, we go down here, we're starting with 53. 53 minus negative 1 gives us, right, minus a negative is actually positive, so we're going to say 54. So we're going to look for an element that has number 54. And when we do that, we get xenon. And that's why this becomes xenon 131. Gamma radiation is simply just electromagnetic radiation. It's very high energy and it has a very short wavelength. So wavelength and frequency are related. This is the speed of light. So this is the wavelength. The frequency is how often it passes. So a wavelength that has a high energy wave might look something like this, where a low energy wave might look something, and don't judge my waves, look something like that. So this would be low energy and this would be high energy. So it happens much more frequently. And then you'll see that E is equal to H times nu. And so if we put, and we said, well, then nu is equal to C divided by lambda, you could say E is equal to H times C divided by lambda. So you can put all those together in one equation if you wanted to get the energy of that wave. We will talk about that later, but not this slide. But when we talk about it being a high energy and a short wavelength, those kind of go together. They're not going to be attracted by positive or negative electrodes because they have no charge, they have no mass, so it's really just a stream of high energy photons. And it almost always accompanies alpha and beta emission, but we rarely show it in nuclear equations. But if you did need to show it, it would look like this. This is gamma, looks like a weird Y with 2 zeros. So positron emission, this is essentially a positive electron, okay? So you can see that written like this, or sometimes you'll see it written as beta positive. If you're new to this, it's better to remember it like this because in that form you'll know what you need to add and subtract. So when we do this, we're starting with potassium 40. We know we're going through positron. It's on the other side of the arrow, so 40 minus, again, 0 gives us 40. 19 minus 1 gives us 18. So when we look at our periodic table, number 18 is argon. So the other element we're going to get is argon 40. So that's positron emission. Now, electron capture is the only one that happens on the left side of the arrow, on the reactant side. And this is where an electron, and we're going to go too deep into this, basically the nucleus captures one of the surrounding electrons and actually converts it into a proton to a neutron. It's kind of cool, but we're not going to go too deep into this. So anyway, this is called electron capture. So the electron's being captured by the nucleus and taken in, and it's going to convert a proton to a neutron. So when we do that, we're taking this electron into the nucleus. So instead of subtracting, now we're going to add. So 197 plus 0 gives us 197. And for mercury, we have 80 plus minus 1, which gives us 79. So it's still going down, but it's because we're adding a negative particle. And then on the right side, we end up with gold 197. These aren't very hard, but the thing is, you have to remember, this is what happens in electron capture. So you're really just going to have to make, flashcards or write it over and over or whatever to remember what it means when I say alpha radiation, beta emission, positron or electron capture. You need to know what those mean. So this is a summary. This would be a great thing to, make flashcards or something like that to study. But you're going to need to know, these for the test, for anything. So when we balance nuclear equations, it's not going to be like anything you've ever balanced before. We're actually going to be balancing the nuclear particles on each side instead of anything else. So we're going to take the sum of what are called nucleons. Nucleons are nuclear particles that are found in the nucleus, so only the protons and electrons. So only I think I might have just said electrons, but protons and neutrons. So only protons and neutrons. That's extremely important. So nucleons are protons and neutrons only. And sometimes we say neutrons with a 0. But protons and neutrons. Electrons are not considered nucleons because they're not in the nucleus. So we're going to be balancing nucleons. And we're going to sum the charges on both sides. Okay, so let's take a look. Write the nuclear equation for the radioactive decay of radium-226. So first of all, we need to know what is radium. And radium is Ra. I'm going to erase that actually. So Ra, and we said it was radium-226, so that's the mass number, goes up here. And if you want, radium is number 88. That's usually pretty helpful. And it's decaying by alpha decay. This is where you need to know that alpha decay is that helium nucleus. So we know there's going to be a helium nucleus, a helium-4 nucleus on the other side. It's what is the other particle? Well, this is the easiest type of problem I can give you because I actually gave you the other particle. But let's figure it out just in case. What's 226 minus 4? Is 222. And what is 88 minus 2? Would be 86. And that would be radon. So I actually told you it was radon 222 in this problem. So you really could have just written that, and I just wanted to know, did you know what a helium particle was? Well, let's say you didn't know what a helium particle was. So you had 226 for radium, 88. You did this. You know this is 222. Sorry. And 86, but you don't know what the other particle over here is. Well, you can do, what is 226 minus 222 would be 4, and 88 minus 86 is 2, and then look up what element number 2 is. So that's how we're balancing it. We always are figuring that out. All right. Potassium 40 is a naturally occurring radioactive isotope. You try this, so pause it and try it. It decays to calcium 40 by beta emission. Do you know what beta emission is? Beta emission is an electron, right? When a potassium 40 nucleus decays by beta emission, it emits one beta particle and gives a calcium 40 nucleus. Write the nuclear equation. So when we do that, we're going to say potassium 40 minus 0. So we end up with potassium 40 minus 0 gives us 40, and 19 minus negative 1. So this is going to go up by 1 to 20, and we get calcium, and then this is our beta particle. Practice it, pause it, and practice it. Technetium 99. So technetium 99 is a long-derived radioactive isotope of technetium. So who can find technetium on the periodic table? It is number 43. So TC 4399. Each nucleus decays by emitting one beta particle. So we're emitting a beta particle. What is our other product? Well, 99 minus 0 is 99. 43 minus negative 1. So 43 minus negative 1 is 44. So what's the product? It's going to be ruthenium, 99. Ah, I put the wrong answer there in my little thingy here, but this is the right answer. All right, so plutonium-239. Plutonium is what? Plutonium-239. So we have to find plutonium on the periodic table, and it's number 94. So plutonium-239 decays by alpha emission, with each nucleus emitting one alpha particle. So we know that alpha emission is that. So what is the other product? 239 minus 4. What's 239 minus 4 is 235. And the other one would be 94 minus 2. So 94 minus 2 would be 92. So this would be uranium-235. So practice these, balance the following equations. Alpha emission from curium-242. So I actually wrote these out for you, and all you have to do is figure out the question mark. Pause it and try it. So 242 minus 4 is going to be 238. And 96 minus 2 is going to be 94. So that will be plutonium. Here we have, so this is alpha emission. Oh, it's already written there. Beta emission, so this is our beta particle here. And we are going to have 28 minus 0 gives us 28. 12 minus negative 1 is 13. So we look for number 13 on the periodic table, and it's aluminum. Now here we have xenon. This is positron emission, so this is going to be a positive electron. And we have 118 minus 0 gives us 118. And 54 minus 1 is 53, which is iodine. All right. That's the end of this chapter.